Do you find that you're getting more and more engineering problems associated with the substance air that we treat as an ideal gas? And if your particular problem involves pretty wide temperature ranges, you're probably going to want to model that air ideal gas as having variable specific heat. And when you do that, you can use table A22, what I call the air tables in the back of the book, to get properties like H, the enthalpy, U, the internal energy, perhaps a property called PR. All of those depend on temperature only. So I'd like to show you a tool that I've built to share with you that I use myself when I need to evaluate air properties when I'm treating air as an ideal gas with variable specific heat. So let's get started. So there's a couple of MATLAB files that I'd like to share with you and show you how they work. Actually, it would be four files, files that are both in SI units and then in English units. The first set would be ideal gas properties of air that I call air tables. The second MATLAB file is specific heats of various ideal gases going beyond air. Remember that for ideal gases, properties such as specific heat, internal energy, enthalpy are functions of temperature only. And so if you model an ideal gas with constant specific heat, this table A20 and A20E give you the pathway to determine a value for specific heat, whether it's CP or CV, depending on the temperature that you decide to model the ideal gas at. So let's look at the air tables first. So welcome to what I'm sharing is the air tables, where I've taken all of these values from table A22 and then in another file A22E, and I've put those into MATLAB as a bunch of sets of vectors. Okay, they're just simply numbers, and let's say in a column. Okay, but then I've added some functions so that if you put in temperature like you do manually, then you can get back a value for enthalpy, internal energy, PR, whatever that is, and VR, whatever that is, and S0, I call that the zero pressure entropy. But remember, of course, it's easy when your numbers match up. It's a little more difficult when let's say your temperature is 283 degrees Kelvin, degrees K, then you've got to interpolate. And that's what those functions that I've created for myself and for you help you to do. So here are the functions that I'm offering. So let's just quickly go over the function list and realize that I've tried to name the functions in a logical way. So for example, this first one, HT underscore kilojoules per kilogram. Well, there's the units. I've tagged all of these function calls with units, because remember, the units are going to be one file will be SI units, another file will be English units. Okay, and then let's look at the first one, HT. Well, that means the output is H with the input of T. And that's the beauty of these ideal gas properties, is that there's a one-to-one correspondence between these properties and temperature. That makes it so much easier than phase change substances like steam. Okay, so you get the idea. HT is the output is H. That's what the function is going to determine. T is what you put in at your temperature. Now, if we drop down, you notice the reverse. Notice the reverse function. Here's TH in degrees K. In other words, that is the output is the degrees, the temperature, where you're putting in H. And I'm hoping that you can think about homework problems or engineering problems where you have determined H. And the question is, well, I need to figure out what the air temperature is when I've determined H. So this would be like the reverse function, input temperature, output H, and on like that. So I hope you get the idea. So this is a set of functions available to you in MATLAB to make your interpolation and lookup easier and faster, as long as you know the fundamentals. Okay, so let's look at the overall organization of the file that I'm going to show you in MATLAB. So the first is a bunch of, the first part of the file is a bunch of comments that I'm explaining what's my source data. I'm showing the reference of my source data, and then I'm giving some instructions to you, myself, reminding myself, how do I use this file? And then I've got some basic user instructions. That's what I just said. Some demo function calls. So this file can stand on its own as a demo, or you can adjust what's going on in the MATLAB file and save as for your own problem. And then finally, the last part of the file, and here's the end of the file. So for this particular file, Airtables, it goes down to line 222. So it's a moderate size MATLAB file. That's the brains behind it, the thermodynamic property functions for air. That's where those reside. I'm showing you screenshots, but we're going to go live to give you a live demo here in a minute. This is a screenshot of the demos of function calls. Look how easy this is. I'm putting in as the user T equals 304, and that's degrees K. Shame on me for not saying what it is, degrees K. Shame on me for not putting units there, okay? But I'm entering the variable name T, the MATLAB variable T, just calling it T, and then I'm calling the function. I'm looking for H. What's the enthalpy at that temperature? Well, I'm using my function call, HT underscore kilojoules per kilogram. My input is T, and I'm getting back H. And then the next part, I'm just preparing the output to the command window. Then finally, let's jump down to this function called PR of T. Well, that's the relative pressure. For those of you that maybe have done some engineering problems, isentropic processes, reversible and adiabatic, involve the property called PR. So if you know T, you can look up PR. And again, I've entered my temperature, 304, and I'm using my function call, PRT. In other words, PR as a function of T, units, non-dimensional, input T. And so I'm getting back PR, and then I'm preparing the output to my command window. So you get the idea of how the demo will work, but if you've got a different temperature, you're interested in getting the properties, H, U, S0, PR, VR, you put in that temperature and you will get a result immediately, complete with interpolation. Okay, command window output. Okay, so if you click your run icon, once you've loaded this file in the MATLAB, here's the result you're going to get. And so you see, my output I'm formatting H with units is 304.2 at an input temperature, degrees K, of 304. And so you get so PR is 1.4 at an input temperature of 304 degrees K. I think you get the idea. And here, let's see. Oh, and if we jump down, let's say PR. Let's say I know PR. I have solved for PR and it turned out to be 2.2. What's the temperature at that value of PR? Well, I bet you say, man, that's kind of cool. I've been doing that a lot here recently. Well, the temperature is 342.2 degrees K. So it's a back calculation. And that function does that for you. Okay, a little bit on formulation of how I created those functions. So here, let's look for enthalpy as a function of temperature. Okay, here's the function. So these little lines in MATLAB represent the entire function called HT underscore kilojoules per kilogram with an input of T, and the output is H. So just a few lines. Well, what I'm doing here in this function is I'm defining the temperature vector that I got from the book. There's values in the book. I'm defining the enthalpy vector, got from the book, copy and paste, okay? And so the function call is very simple. I'm using the built-in function in MATLAB, interp1. This is my x vector, temperature. This is my y vector, enthalpy, and my input x is temperature. And so I'm interpolating to find my output y, which in this case is h. So I think you get the idea. So each one of these functions, especially for air as an ideal gas, it's just really so easy to create function after function after function to automate your manual lookups. Okay, that was that file. That was the Airtables file. Now I'm pausing because I'm moving on to another MATLAB file. And this MATLAB file is called ideal gas specific heat underscore SI. So you get your SI units here. All I'm doing here is I've copied and pasted values from table A20 from multiple ideal gases, air, nitrogen, oxygen, carbon dioxide, carbon monoxide, and hydrogen. I've loaded all of those CP properties, all the CP properties into MATLAB. Right? So let's look and see how that works. Here's the intro. Okay, this is the intro. And what the user does, let's see if we can look at the comment. It says, user specifies ideal gas substance and temperature. So the user, either you or me, we're going to enter a string that will describe the substance. It might be AIR or CO2. You get the idea. And the temperature in degrees K. And the command window output is going to say, well, this is what you put in for the ideal gas CO2 at a temperature of 311. Here are your properties. CP at that temperature for carbon dioxide, CP is 0.857 kilojoules per kilogram degree K. CV is 0.668 kilojoules per kilogram degree K. R is this, okay? And K, which is always CP over CV, is simply dividing one lookup number by the other, 1.3. So you get the idea of this basic, simple lookup tool that you can use for table A20 lookups. Okay, and so just let me look at my title. Basically a single function is used. Oh, this is a little different than my steam tables and even the air table. So let's look at the function. Notice here on this function, the output, there are 4 outputs and they're in brackets. I've just learned this recently, learning how to use MATLAB. So I've been at this now for about 3 weeks. So I've learned that a function can have multiple outputs, in this case, 4 of them. They are CP, CV, R, and K in brackets. So the 4 variables are coming out. 2 variables are going in. One is called a gas ID, and the other is temperature T. So the gas ID is a text, and this, you, the user, yourself or myself, we're going to put in with little single tick marks any of these strings, but it can only be those strings. So if you put in, air, nitrogen, oxygen, CO2, CO, H2, helium, neon, and argon. Those are monatomic ideal gases. So if you put in something other than those, it's going to blow up on you and give you an error message. You have to put one of those strings will work, and then you put in the temperature and the outputs. I think I just covered CP, CV, R, and K. Okay, so you get the idea. All right, and so here is a demo. I'm putting in T is 311 degrees K. The gas ID is CO2. So you see I'm putting in little single tick marks around the text, CO2. Here's my function call. So that's what I enter as the user. Here's my function call in brackets, 4 variables that I've just decided I'm going to call those variables. And here's the function call, IG specific heats underscore SI. and the user inputs gas ID, string, and temperature value. So set of 4 variables in the bracket is provided from the function call, and notice those brackets being used. And then, of course, here's the output. Here's the command window output. Once I hit the run button for the demo, I get this result right here in my face. I could either continue solving the problem in MATLAB, or I could scratch those numbers down on pencil and paper and do my solution on pencil and paper, whichever you have in mind doing. I've been teaching myself how to use graphics in MATLAB. I'm getting a little better at it. So in this demo, I've decided to plot CP versus temperature for the ideal gas air. And so in the demo, I've added a little MATLAB code where I'm showing myself I can do this. Okay, I've labeled this figure 1. Okay, I've put in the temperature vector and the CP of air vector. I'm doing that up in the body of MATLAB. Okay, and then I'm preparing the plot. So it's pretty neat that all I have to do in MATLAB is say plot x-axis vector, temperature in degrees K, y-axis vector, air CP, just 2 vectors to plot, x and y. I am titling my plot, which is always a good idea to do. I'm labeling my x-axis, temperatures degree K. I'm labeling my y-axis, and I'm turning my grid off to keep my plot as simple looking as possible. And of course, the interesting engineering result is this is data that's plotted. It's right out of your table A20. And you can observe that for large changes in air temperature, there's a large, about a 10% change in C sub P. It looks large, right? Because you look at these numbers, 1 to 1.15. So in the whole scheme of things, you're looking at about 10 to 15% variability in C sub P, value for C sub P. Okay, so anyway, that was my foray into plotting. I'm getting a little better at plotting in MATLAB. Oh, so this is my cue to go live, so I can give you a little demo of the Airtables and then also show you how to access these files out on Jay's Toolbox. Okay, I'm going to minimize PowerPoint. I'm going to go to MATLAB. Okay, let's see. Let's look at air props functions SI. I just loaded those in from my folder. Okay, here we are. Okay, here is my introductory remarks. Here is the function list that's available to you, the user, and to me. Here's my demo. And so let's just look at and so I'm entering 304. I'm calling my function h of t. H is a function of t, kilojoules per kilogram, inputting t, 304, and getting back h. And here I'm preparing my command window output. Here, I've got to move my Zoom stuff around here. Just excuse me a second. I've got to move my output, my Zoom, so I can get to my run button. There we go. Let's see. We'll PR. You're using relative pressure a lot for isentropic reversible adiabatic processes. I'm entering the temperature where I've got to look up P sub R. I'm calling the function. Very simple. Look how simple this is in the body, okay, of the MATLAB file, okay? And then I'm preparing my output, just like this. So you get the idea. What are the function? Okay, so let's go ahead and run the demo. And we'll look at, and there's the command output. So for air, these are different function calls. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9 function calls, depending on what you, the user, me, wish to enter. And you get a numerical result right then and there, complete with interpolation. So that's the demo. Let's see the brains behind this. I'm going to keep scrolling down beyond the demo programming. And here's the function library. So if you open this file, remember, don't change anything below the function library. If you do, you're on your own. Okay? But these are the functions that I've created for you and for myself in order to quickly evaluate properties of air. Okay, so you get the idea. Here's the entire function call for H as a function of T is right there. Okay, all I'm doing is I'm reading in the temperature vector from table A20. I'm reading in the enthalpy vector, table A20, and then in one single MATLAB command, I'm doing the interpolation for the X vector is T, the Y vector is H, and my input is the single temperature. And the functions go on and on from there, but not that big of a file, a little over 200 lines. Okay. You say, oh, this looks worth a look. Okay. So let me go ahead and minimize MATLAB just to save time. I will not demonstrate the C sub P lookup. I think you can follow along. You can figure that out on your own. So let's go to my browser and let's go to Jay's Toolbox. So Jay's Toolbox is here at jaystoolbox.vt.domains. And I've got a single page for the MATLAB library. We'll scroll down a little bit and we'll drop down Toolbox and click on MATLAB. We'll click on MATLAB. There we go. Okay. And we'll scroll down this one page. Oh, look at this, top of the page. Air props English, air props SI. Okay. So these are the air tables. So all you have to do is just click on, just download this file. And then, now, this file, of course, is saved in I had to save it in the .doc file type. It's the only way I could save this to my website. Okay. You need to open this file in Notepad and save as a .m file to get it into the MATLAB format, so you can load it in MATLAB. But either English or SI units for air properties. And here is ideal gas specific heats. So what we were looking at here in that second part was ideal gas CP in SI units. And all you got to do is click this to download the file, and then you get the drill. So there's some other demos. So for example, I have come up with an example problem of using the air tables. I call it air compressor MATLAB, where I am taking a real air compressor and determining the isentropic work, W dot over M dot, and also the actual work, W actual over M dot, and I've given a certain compressor efficiency. So that's how you get to these files to download them. Jay's Toolbox, MATLAB, and then just scroll down to select the file, MATLAB file you'd like to download. Okay, so let's see if I can figure out how to get back to PowerPoint. I made it. We've done the live video. Okay. And so let's recap. I'm giving you separate files, separate MATLAB files for SI and English units. Be aware of that. You can use these demo files as either standalone thermodynamic property getters, either for air properties or C sub P, the other specific heat type related properties. Or you can save as that file to address your own problem solving requirements. So you do a little head scratching and think about, how could I just click save as, rename that file so you don't lose the original file that you've got on your PC, and then somehow tailor the MATLAB programming block instead of the demo. How would you create your own MATLAB commands to either solve a problem or simply just get the properties that you're interested in, or in the format that you'd like? Oh, and then one last remark, of course, is you need to fully understand the fundamentals of working with ideal gases before getting into this MATLAB tool. Very dangerous just to blindly use someone else's MATLAB file if you really don't know what's going on. So I really, really want to encourage you to get the fundamentals, ask questions in class if you don't understand the fundamentals, because I want you to feel comfortable using these MATLAB tools. And the way to feel comfortable using them is to fully understand what's behind them. So there you go. Download one of those Airtables files. Download one of the C sub P files. Give it a test ride. See if it might help you save you time in your problem solving and improve your effectiveness.